In the previous video on the hierarchical linear model, we simply looked at a way in which we can decompose levels of social trust into individual and country level components. But there were no predictor variables in that analysis, and now we would like to add an individual level predictor to the model in the form of political efficacy. And what we would like to do is turn that resulting model into a random coefficient model. In general, random coefficient models are models, linear models typically, that allow the effects of predictors to vary across contexts. Now, in the simplest setup, actually the only thing that varies by context is the intercept, and that is where we will start. In our case, letting the intercept vary across countries means that we say that the baseline of social trust varies across countries. We also add political efficacy there, so the individual deviations from that country level baseline are at least partially understood in terms of the respondent's level of political efficacy. We actually only register whether the baseline of social trust varies across countries. We don't yet have actually any kind of explanation of that, and we will get to that in the next video. So following the idea that we talked about the last video of creating level 1 and level 2 models, let's actually continue with that, and let's actually create this level 1 model here. So what we have is a same old error term that we had before, epsilon sub IC, which we believe to be normally distributed with around a mean of 0 and a standard deviation of sigma. But the model for y is a little bit more complicated than it was before. We're saying y sub IC equals beta 0c plus gamma 10 xic plus epsilon IC. So we're saying there's a beta 0c, that's an intercept, and because that has a subscript c, it means that actually the intercept is allowed to vary across countries. We have also an effect of political efficacy, which is our xic in this model. But you notice that the coefficient associated with xic is a gamma 10. There is no subscript c in that gamma. So we assume that political efficacy plays out exactly the same way across all countries. Theoretically, we would expect that more efficacious individuals are also more trusting. So we expect gamma sub 10 to be positive, but we don't expect there to be variation in that across countries. Now, for the level 2 model, things look very similar to what we had in the random effects ANOVA. Basically, what we're writing there is simply, again, the same as in random effects ANOVA, that beta 0c equals gamma 00 plus delta 0c. Here we would not interpret gamma 00 as a grand mean, but as a grand intercept. The intercept that holds for all respondents in all countries. And delta 0c, just like it was in the random effects ANOVA, is assumed to be normally distributed around a mean of 0 with a standard deviation of the square root of tau 00. Now, what actually is useful, and we didn't do that in the previous video, is actually now to substitute the level 2 model into the level 1 model. That creates what is known as a mixed model. So in this particular setup, the mixed model is going to be y sub IC equals gamma 00 plus gamma 10 xic plus delta 0c plus epsilon IC. The gammas here are called the fixed effects. They no longer have a subscript c unlike the betas. They are therefore constant, that is fixed, across units I and clusters, countries C. Now, as far as the assumptions go in this particular model, we actually have the same exact assumptions from the random effects ANOVA concerning exchangeability and a lack of correlation between the level 1 and level 2 error terms. The delta is known as a level 2 error term, the epsilon is a level 1 error term. We have to add one more assumption here, and that is that XIC is weakly exogenous. You may remember that assumption from regression analysis. It was important there, it's important here as well. So let's see what this brings when we actually run this. So if you compare the syntax from LME4 to the syntax from the random effects ANOVA, you'll notice that actually the only thing that really has changed is that right after the tilde behind social trust, I've replaced the 1 with pol F, political efficacy. But the rest of the model equation looks exactly the same as it did before. Because the only thing that we have actually changed here relative to the random effects ANOVA is that we have added political efficacy as a predictor of social trust. So if we run this, now we get the following estimates. We now have two fixed effects, an intercept, that's sort of the baseline you could say, and an effect of political efficacy that indeed turns out to be positive in this particular situation. So more efficacious people indeed are more trusting of other people. And then we have some country level standard deviation. We expect that to be more or less the same as it was in the random effects ANOVA because we haven't really changed anything that can account for the intercept variation. And we have some residual variation that we do actually expect to have gone down a little bit because we now have added an explanation for why individuals, actually some individuals are more trusting than others. It's not much of an explanation, it's just one predictor variable, but theoretically we should assume that this error variance is a little bit less than it was in the random effects ANOVA model. But we've made an assumption here, and the assumption is that the effect of political efficacy is actually the same across all contexts, all countries. That in a sense, the trust that you have in your own democratic capabilities and the democratic capabilities of the political system in your country basically affect social trust in exactly the same way everywhere. Let's relax that assumption. Now we go to a different random coefficient model where we actually let both the intercept and the slope associated with political efficacy vary across contexts. So what we're going to do here is we're going to actually write up a model that is going to be a bit more complicated than what we had before. The level 1 model is one place where you immediately start seeing a change. Y sub IC, so that's the trust of individual I in country C, is equal to an intercept, beta 0c, that we had also in the random intercept model. But now you'll notice that the effect associated with political efficacy, XIC, is also written with a subscript C. Beta 1c is the effect of political efficacy. And because there is a C in the beta, it means that we're basically saying the effect of political efficacy does not have to be the same across all countries. And then, of course, we have the usual individual or level 1 error term, epsilon IC. Now, the level 2 model is also going to change, because notice that we have now two random coefficients here. Beta 0c, because it varies across C, is a random coefficient. But now also beta 1c is a random coefficient. So what happens is that now our level 2 model actually requires us to write two equations. An equation for the intercept and an equation for the slope. So the intercept equation is going to be the one that we have seen before. Beta 0c equals gamma 0 plus delta 0c. So we're saying basically whatever the intercept in country C is, it's equal to some common intercept gamma 0 plus some deviation of that common intercept that is specific to the country, and we call that delta 0c. We did not have a slope equation before because we did not actually have a random effect for political efficacy before, but now we do. So we write an analogous equation here for beta 1c. Beta 1c equals to gamma 10 plus delta 1c. So gamma 10 here is a common slope, say the effect of political efficacy across all countries. And then there's a deviation in that effect that is equal to delta 1c. Which is another level 2 error term. So now we have two level 2 error terms, delta 0c and delta 1c. And that means that our distributional assumption is going to get a little bit more complicated. We're going to now say that the joint distribution of delta 0c and delta 1c is a normal, a bivariate normal distribution in this case. We're still going to assume that each error term has a mean of 0, but instead of specifying just variances for each of these error terms, we now have to specify a full covariance matrix. The full covariance matrix here means we have to specify a variance in the intercepts, which is tau 0, a variance in the slopes, that's the variance of delta 1c, we call that tau 1. But there's also a covariance here, tau 1, that is basically capturing the relationship between the intercepts and the slopes. Very often we see that that's actually a negative covariance. It usually is not 0, so we don't want to typically restrict this element to be 0. And therefore actually what we do is we usually estimate it. Now, importantly here you might say is, well, why is this here left blank? Well, it's left blank because it's the same thing as this tau 1. So I just show you the non-redundant elements of the covariance matrix here. Now, we can again substitute these level 2 equations into the level 1 model to create what we know to be a mixed model. And that's now going to look like this. YIC equals gamma 0 plus gamma 10 XIC, that should be, plus delta 0c plus delta 1c times XIC plus epsilon IC. The last three terms here are all error terms. And the first two terms are the fixed effects. So what does that even look like, a random slope and intercept model? Well, if you would graph the regression lines for different countries, different groups, what you would see is they cross the y-axis at different points. That's the variation in the intercepts. And they also have different slope coefficients. Here we have a situation where 3 out of the 5 lines have a positive slope. One has a slope that is practically indistinguishable from 0. So this would be a group where x really has no bearing whatsoever on the outcome. And here we even have a situation where the effect of x reverses to be negative. So increases in x in that context, in that group, are associated with decreases in the expected value of the outcome variable. Now, there is many things that we can look at here. Because if we look at this mixed model, we see that there's a fairly complicated error term here at the end. We also can then think about what that implies for various moments. So if we do that, we could start by looking at the average score of YIC. So we just take the expectation over YIC, carry that through the mixed model equation, and what you're left with is gamma 0, 0 plus gamma 0, 1 times XIC. So this gives us the prediction of the average individual I in the average country C given some value X of political efficacy. Now this is something that we can look at. This is the typical way we would interpret a model of this nature, but I actually find it often quite interesting to also start looking at other things that the model implies. For example, what is the variance of Y? Where do we expect to see the biggest variation? And mathematically, you can derive that the variance of YIC is equal to the variance in the intercept plus 2 times the covariance between the intercepts and slopes times x plus the variance in the slopes times x squared plus this sigma squared. That is the individual level variance. So you'll notice that now the variance here is a function of x. This is now a deviation from the idea that the variance of y is constant across units. What is also, of course, no longer true is that actually the observations are independent. If I take 2 units from different countries or different clusters, more generally, then it is indeed still the case that we assume that the covariance between their scores is 0. But if we take 2 individuals from exactly the same cluster, say exactly the same country, then the covariance between respondent I and respondent J from that particular country C is equal to tau 0, 0 plus tau 0, 1 times the sum of their x's plus tau 1, 1 times the product of their x's. And that is typically not equal to 0. How would we implement that in R? Quite simply, we just change the last bit of the syntax. We replace the 1 bar country by pol F bar country. And what now is going to happen is that R will estimate a variance of the intercept, a variance of the slope, and it doesn't actually give us the covariance between the intercept and the slope, but it will give us the correlation between the intercept and the slope, which is often actually more telling. So here are the estimates. Here you now see the intercept. This is my gamma 0, 0 estimate. Here is my gamma 1, 0 estimate. But what I'm particularly interested in is what is happening here. This is the variance in the intercepts. That's sizable. This is the variance in the slopes. That's much smaller. So maybe we were wrong in assuming that the effect of political efficacy really varies that much across countries. We could actually test that, but that's for a different video. And here is the correlation between the intercept and the slope. And of course, we still also have the residual variance. The variance that remains in the responses of individuals even after we have considered the differences in political efficacy.